we can discuss singularities and zeros. A singular point of an analytic function f of z is a point z0 at which f of z ceases to be analytic. That means a singular point is a point at which the function is not analytic. The function f of z is not analytic. Now, what is meant by 0? 0 of the function f of z is a point at which f of z equal to 0. Lorentz series is used for classifying singularities, whereas the Taylor series is used for discussing zeros. Now we can discuss isolated singularity. A singular point z0 of a function f of z is said to be isolated singularity if there is some neighborhood of z0 throughout which f is analytic except at the point z0 itself. That is, z0 is isolated singular point if there is no other singular points in the neighborhood of z0. For example, consider the function f of z is equal to 1 by z. Now, to find the non-analytic point, we can equate the denominator to 0. So, z is equal to 0 is a singular point. Now, z equal to 0 is the non-analytic point and there is no other non-analytic point in the neighborhood of z is equal to 0. So, z equal to 0 is an isolated singularity. Okay. Now, another example, f of z is equal to z plus 1 divided by z cube into z square plus 1. Now, you equate the denominator to 0 to find the non-analytic points. So, you have z is equal to 0, 1, minus 1. So, we have these are the isolated singularities. Now, another example, f of z is equal to tan z. Now, tan z means sin z by cos z. Now, the non-analytic points are given by cos z equal to 0. That means z is equal to plus or minus 2n plus 1 into pi by 2, where n equal to 0, 1, 2, 3, etc. Okay, so what are the non-analytic points now? Z is equal to plus or minus pi by 2, plus or minus 3 pi by 2, etc. are the isolated singularities. Now another example, consider tan 1 by z. Okay, so here we have tan 1 by z means sin 1 by z by cos 1 by z. Now the non-analytic points are given by cos 1 by z equal to 0. So we have 1 by z is equal to plus or minus 2n plus 1 into pi by 2. So what is z? Z equal to plus or minus 1 by 2n plus 1 into 2 by 5. That means what are the points here? Plus or minus 2 by pi, plus or minus 2 by 3 pi, etc. So these are the singular point of the function tan 1 by z. Next we can consider the function 1 by sin pi by z. So the singular points are given by sin pi by z equal to 0. And we know when sin theta equal to 0, theta equal to n pi. So, pi by z is equal to n pi. So, we have z is equal to 1 by n, where n varies from 0, plus or minus 1, plus or minus 2, etc. Actually, here we cannot take 0 because 1 by 0 will come. Okay. So, here we can take a z is equal to 1 by n, where n takes the values 1, 2, 3, etc. Plus or minus 1, plus or minus 2, plus or minus 3, etc. So when we substituting the different values, here we have the singular points are, when n become very large, we will have z is equal to 0. Okay. Similarly, when n is equal to 1, you have 1. When n is equal to minus 1, etc. So we have 0 and 1 by n, where n varies from plus or minus 1, plus or minus 2, etc. are the singular points. Okay. Now here you can see that z equal to 0 is a non-isolated singular point, because there are so many singularities in the neighborhood of z is equal to 0. All other singularities lies between minus 1 and 1. Okay, so all other singularities between minus 1 and 1 are isolated. Z equal to 0 is non-isolated. Okay. Now let us consider the classification of isolated singularities using Lorentz series. Now we can, if we have a function f of z, we have the Lorentz series expansion. F of z is equal to sigma an into z minus z naught whole raised to n plus sigma bn divided by z minus z naught whole raised to n. Here n varies from 0 to infinity, and here n varies from 1 up to infinity. This Lorentz series is valid in the neighborhood of the singular point z equal to z naught except at z naught itself. The sum of the first series in equation star is analytic at z equal to z naught, and it is called the regular part of f of z in the neighborhood of z naught. So what is the regular part? So this one is the regular part of f of z. Now the negative powers of z minus z naught is contained in the sum of the second series, and it is called the principal part. Principal part. If the principal part contain only finite number of terms of the form b1 by z minus z naught plus b2 by z minus z naught whole square plus etc. plus bm divided by z minus z naught whole raised to m with bm not equal to 0, then z equal to z naught is called a pole of order m. Pole of order m. So here the highest power of z minus z naught is m. Okay. So z equal to z naught is called a pole of order m. Poles of order 1 are called a simple pole. If the value of m is 1, that means we have the coefficient of 1 by z minus z naught. Now poles of order 1 are called a simple pole. If the principal part contain infinitely many terms, then z equal to z naught is called a isolated essential singularity. Isolated essential singularity. Okay. So we have three terms here. First one, simple pole. That means here the principal part contain only one term. That means the highest power of z minus z naught is 1. That means pole of order 1. Okay. Now if the principal part contain infinite number of terms, then z equal to z naught is called an isolated essential singularity. Okay. Now what is poles of order m? Now if the principal part contain m terms like bm divided by z minus z naught raised to m, then we can see that the highest power of z minus z naught is m. So in that case we can call z equal to z naught as a pole of order m. Now let us move to some examples. First consider f of z is equal to 1 by z into z minus 2 raised to 5 plus 3 by z minus 2 the whole square. Now to find the singularities, we can equate the denominator to 0. Thus we have z equal to 0 is a pole of order 1. So z equal to 0 is a simple pole. Whereas z equal to 2 is a pole of order 5. Okay, so the highest power of z minus 2 is here 5. So z equal to 2 is a pole of order 5. Whereas the highest power of z is 1. So z equal to 0 is a pole of order 1. That means it is a simple pole. Okay. Now another example. F of z is equal to e raised to 1 by z. Now you can expand this 1 plus 1 by z into 1 factorial plus 1 by z square into 2 factorial plus etc. Now here you can see that the principal part contains infinitely many terms. Principal part means the negative power of z. Okay, so there are infinitely many terms in the principal part. So we can say z equal to 0 is an isolated essential singularity. Now next example, sin 1 by z. And we know what is sin z? Z minus z cube by 3 factorial plus z raised to 5 by 5 factorial, etc. So here we have, instead of z, here we have 1 by z. So 1 by z minus 1 by z cube into 3 factorial plus 1 by z raised to 5 factorial minus etc. Here also the principal part contains infinitely many terms. So z equal to 0 is an isolated essential singularity. Okay, now we can move to the next example now. Consider f of z is equal to sin z divided by z raised to 5. So you just expand this. So 1 by 5 z raised to 5, then z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus etc. Now you can take this 1 by z raised to 5 inside the bracket. So 1 by z raised to 4 minus 1 by z square into 3 factorial plus 1 by 5 factorial minus z square divided by 7 factorial plus etc. So here you can see that z equal to 0 is a pole of order 4 because the highest power of z, that means 1 by z, the highest power of 1 by z is 4. Highest power of 1 by z is 4. So we have z equal to 0 is a pole of order 4. Okay. Now another example, 1 by z cube minus z raised to 4. Here you can take z cube outside, so 1 minus z. Then 1 by 1 minus x model. Now you can expand that. That is 1 plus x square plus etc. Now you can take that z cube inside. 1 by z cube inside the bracket. So 1 by z cube plus 1 by z square plus 1 by z plus 1 plus z square plus etc. Okay. Now here you can see that z equal to 0 is a pole of order 3 because the highest power of 1 by z is 3. That means the highest negative power, highest terms. So here we have to consider the highest power of z minus z naught. Actually here we are considering the negative powers in the principal part. Okay, so z equal to 0 is a pole of order 3. Now another example, z square minus 2z plus 3 divided by z minus 2. So this is same as, now you can write the numerator as z minus 2 into z plus 3 divided by z minus 2. Now this is same as z plus 3 by z minus 2. Now this is same as z plus 3, yes, it is enough, 3 by z minus 2. Now this expansion is valid for 0 less than mod z minus 2 mod z minus 2 greater than 0. So here we can see that z equal to 2 is a simple pole. That means pole of order 1. So this is a simple pole. Now another example, sin hz divided by z raised to 4. This is 1 by z raised to 4 into z plus z raised to 3 by 3 factorial plus z raised to 5 by 5 factorial plus etc. Now you can take this z raised to 4, 1 by z raised to 4 inside the bracket. So here we have 1 by z cube plus 1 by z 3 factorial plus z by 5 factorial plus etc. Okay, so here what is the highest power? That means the negative power of z. The highest negative power of z is 3. So you can see that z equal to 0 is a pole of order 3. Okay. Now we can consider another example now. One by z square into 1 plus z. This is same as 1 by z square, then 1 by 1 plus z. That is 1 minus z plus z square minus z cube plus etc. And this expansion is valid for mod z less than 1. 0 less than mod z less than 1. Now you can take this 1 by z square inside. So 1 by z square minus 1 by z plus 1 minus z plus etc. And this expansion is valid for 0 less than mod z less than 1. Therefore, z equal to 0 is a pole of order 2. Okay. Now another example. Suppose f of z is equal to 1 by z square. Then here we can see that z equal to 0 is a pole of order 2. Okay. Now if we are considering the modulus of f of z, that is equal to 1 by z square, modulus of this function, and that is equal to 1 by mod z square, and that tends to infinity as z tends to 0. When z equal to 0, mod z is 0, so 1 by 0, so that function tends to infinity. Okay, now we have a theorem related to this example now. That theorem says if f of z is analytic and has a pole at z equal to z naught, then mod f of z tends to infinity as z tends to z naught, in any manner. Okay, let us discuss the Picard's theorem. If f of z is analytic and has an isolated essential singularity at a point z0, it takes on every value with at most one exponential value in an arbitrarily small epsilon neighborhood of z0. We can discuss one illustration now. Consider e raised to 1 by z, that is equal to 1 plus 1 by z into 1 factorial plus 1 by z square into 2 factorial plus etc. Here we can see that in this expansion there is an infinite negative powers of z. So z equal to 0 is an essential singularity. E raised to 1 by z assumes the value minus 1 an infinite number of times in each neighborhood of the origin. E raised to z is equal to minus 1 when z is equal to 2n plus 1 into pi I, where n equal to 0, plus or minus 1, plus or minus 2, etc. Then e raised to 1 by z is equal to minus 1 when z is equal to 1 by z minus 1 into pi I, where n equal to 0, plus or minus 1, plus or minus 2, etc. So e raised to 1 by z is equal to minus 1 when z is equal to minus I by 2n plus 1 into pi. Where n varies from 0, plus or minus 1, plus or minus 2, etc. Okay, and an infinite number of these points clearly lie in any given neighborhood of the origin. Since e raised to 1 by z is not equal to 0, for every value of z, 0 is the exponential value in Picard's theorem. Now, for studying the behavior of f of z at z is equal to infinity, it is enough to study the behavior of f of 1 by z at z is equal to 0. So this is a very important point. So in order to study the behavior of the function f of z at z equal to infinity, it is enough to study the behavior of the function f of 1 by z at z is equal to 0. Okay. Now, let us consider one example. Prove e raised to z has an isolated essential singularity at z equal to infinity. So our function is f of z is equal to e raised to z. So in order to study the behavior of the function e raised to z at z equal to infinity, we already taught it is enough to study the behavior of the function f of z at z equal to 0. So e raised to 1 by z means e raised to 1 by z. Now we can consider this expansion. Now here you can see that the principal part contains infinite number of terms. Therefore z equal to 0 is an isolated essential singularity of e raised to 1 by z. Okay, z equal to 0 is isolated essential singularity of e raised to 1 by z, and hence z equal to infinity is an isolated essential singularity of the function e raised to z. So this is one approach. Now another one, identify the singularity at a given point. So here consider one example, 1 minus e raised to z at z equal to 2 pi I. Now our function is f of z is equal to 1 by 1 minus e raised to z. Now the poles are given by equating the denominator to 0. That means e raised to z is equal to 1. That means z is equal to 2n pi I, where n equal to 0, plus or minus 1 plus or minus 2, etc. So z is equal to 2 pi I is a simple pole. Okay, now we can consider another example. Example number 2. Consider cot pi z divided by z minus a whole square at z equal to a. So this is our given function. Okay, now cot means cos by sine. So this is same as cos pi z divided by sine pi z then into z minus a the whole square. Okay, now poles are obtained by equating the denominator to 0. So we have sine pi z into z minus a the whole square equal to 0. That means sine pi z equal to 0 or z minus a the whole square equal to 0. So here we have sine theta equal to 0 implies theta equal to n pi. Okay, so we have z is equal to n. And here you have z equal to a twice. Okay, so what are the possible values here? So here we have z is equal to n, where n equal to 0, plus or minus 1, plus or minus 2, etc. And z is equal to a are the poles. Now another example, f of z is equal to 1 by sin z minus cos z. Z is equal to pi by 4. Now when we equating the denominator to 0, we have sin z minus cos z equal to 0. That will give you the poles. So we have sin z equal to cos z. That means sin z by cos z equal to 1. That means tan z is equal to 1. That means z is equal to n pi plus pi by 4, where n is equal to 0, plus or minus 1, plus or minus 2, etc. Therefore, z is equal to pi by 4 is a simple pole. Okay. Next you consider next example, sin 1 by 1 minus z at z equal to 1. So here you can expand this using the expansion of sin z. So z minus z cube by 3 factorial, z cube by 3 factorial plus z raised to 5 by 5 factorial minus etc. So here we can see that z equal to 1 is an isolated essential singularity. Why? Because the principal part contains infinite powers of 1 minus z. Now let us move to the next singularity, that is known as removable singularity. Removable singularity. A function f of z has the removable singularity at z equal to z0 if f of z is not analytic at z equal to z0, and it can be made analytic by suitably defining f of z0. For example, f of z is equal to sin z divided by z, and here define f of 0 equal to 1. Then expanding, you can see that this is z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus etc. Okay, so that is equal to 1 minus z square by 3 factorial plus z raised to 4 by 5 factorial minus etc. So z equal to 0 is a removable singularity. Here there is no z term in the denominator. That is removed here. So that is why the name removable singularities. Now let us move to more examples now, identifying the singularities. So the question is, identify the singularities of this function. So we can expand this 1 plus 1 by z into 1 factorial plus z square into 2 factorial plus etc. So that is equal to z plus 1 plus 1 by z into 2 factorial plus 1 by z square into 3 factorial plus etc. So here you can see there are infinitely many negative powers of z. So z equal to 0 is an isolated essential singularity. Okay. Now another example. Consider z square divided by 1 plus z. This is equal to z square into 1 minus z plus z square minus etc. So this is equal to z square minus z cube plus z raised to 4 minus etc. And here there is no z term in the denominator. So z equal to 0 is a removable singularity. Now we can consider another example. Cos z divided by z. Now we can expand this 1 minus z square divided by 2 factorial plus z raised to 4 by 4 factorial minus etc. Now you take 1 by side inside the bracket. So we have this expansion. So here you can see that z equal to 0 is a simple pole. That means a pole of order 1. Okay. Now let us consider one more example. 1 minus e raised to 2z divided by z raised to 4. So we can expand this 1 minus. Now we can write the expansion of e raised to z, e raised to 2z plus etc. Then whole divided by z raised to 4. Now here 1 minus 1, that is 0. Okay, so minus of the remaining terms. So 1 by z raised to 4 into minus 2z by 1 factorial minus 4z square by 2 factorial minus 8z cube by 3 factorial minus etc. Now you take that 1 by z raised to 4 inside the bracket. So we have that is equal to 1 by, here we have minus 2 by z cube into 1 factorial minus 2 by z square minus 4 by 3 z minus etc. And here you can see that now here in this expansion you can see that z equal to 0 is a pole of order 3. Pole of order 3. Okay. Now let us move to zeros of analytic function. Zeros of analytic functions. A zero of an analytic function f of z in a domain capital D is a point z equal to z0 in capital D such that f of z0 equal to 0. A 0 has order n. 0 has order n if f of z naught, f dash z naught, etc. f n minus 1 z naught are all equal, but f n of z naught not equal to 0. That means the nth derivative not equal to 0 and all other derivatives are equal, and that value become 0, equal and that equal to 0. Okay. Now a 0 of order 1 is called a simple 0. Simple 0 means a 0 of order 1. Now for second order 0, for second order 0, for second order 0, f of z naught equal to f dash z naught and that value equal to 0. But f double dash of z naught not equal to 0. So this is the method of finding the order of 0. Now let us move to one example now. Consider the function f of z is equal to 1 plus z square. Now you find its derivative. F dash z equal to 2z. Okay. Now f of z equal to 0 implies z square is equal to minus 1. So z is equal to plus or minus square root of minus 1. That means plus or minus I. Okay. Now you find what is f of I. F of I is 0. What is f dash of I? F dash of I 2I not equal to 0. Similarly, what is f of minus I? 0. And f dash of minus I is minus 2I. That is also not equal to 0. So here we can say z equal to I comma minus I are simple zeros. That means 0 of order 1. Now we can consider another example. F of z is equal to 1 minus z raised to 4 the whole square. Now here we have 1 minus z raised to 4 the whole square equal to 0 implies 1 minus z square equal to 0 twice. So z square is equal to 1. So z equal to plus or minus root 1. Root 1 means 1. So plus or minus 1, and also here we have not z square. Z raised to 4 is equal to, here z raised to 4 is equal to 1. So the possible values are plus or minus 1 and plus or minus I. Okay, so these two values z equal to, these four values plus or minus 1 and plus or minus I are zeros of order second order. 0 of second order. Zeros of second order whole square equal to 0. Okay. Now let us consider third example. F of z is equal to z minus a whole power 3. So here we can see that z equal to a is a 0 of order 3. Now another example. F of z is equal to e raised to z, and e raised to z is never 0. So this function e raised to z has no zeros. Now another example. F of z is equal to sin z. We have f dash z is cos z. Now f of z equal to 0 implies sin z equal to 0. So what is f of 0? F of 0 is 0. What is f dash 0? F dash 0 is 1, not equal to 0. Okay, so 0 is a 0 of order 1. Now sin z equal to 0. F of z equal to 0 implies sin z equal to 0. And sin z equal to 0 implies z is equal to n pi, and n is an integer. Okay, so what are the possible values of z here? Z equal to 0, plus or minus pi, plus or minus 2 pi, etc. are the zeros of the function sin z. Now we can consider another example. F of z is equal to sin square z. Here the zeros are z equal to 0, plus or minus pi, plus or minus 2 pi, etc. are zeros of second order. Zeros of second order. Next we can consider another example. F of z is equal to 1 minus cos z. Now zeros are given by f of z equal to 0. That means 1 minus cos z equal to 0. That means cos z is equal to 1. That means cos z equal to cos 0. So z equal to plus or minus 2n pi plus alpha. Here the value of alpha is 0. So plus or minus 2n pi only, where n belongs to z. So what are the possible values of z here? 0, plus or minus 2 pi, plus or minus 4 pi, etc. Okay. Now here we have our function is f of z is equal to 1 minus cos z. Now you can find this derivative f dash z, that is sin z. Now f double dash z, that is equal to cos z. Now we can find the function values. F of 0 is 0, f dash 0 is 0, and f double dash 0 is 1, not equal to 0. Therefore f of z has 0 of order 2. Okay. Now we can consider another example now. Suppose f of z is equal to 1 minus cos z the whole square. Then what is f of 0? Here you can see that f of 0 is 1 minus cos 0. Cos 0 is 1. So f of 0 is 1 minus 1 the whole square, that is 0. Now you find its derivative f dash z, that is 2 into 1 minus cos z into sin z. Now what is f dash 0? F dash 0 is again 0. Now you find the second derivative f double dash of z, that is equal to 2 into 1 minus cos z into cos z plus sin square z. And what is f double dash of 0? Equal to 0. Now f triple dash of z equal to 2 into minus 1 minus cos z into minus then cos z into sin z plus 2 sin z cos z. And f triple dash of 0 is 0. Now f fourth dash of z equal to 2 into minus of 1 minus cos z into cos z minus sin square z plus 3 times cos square z minus sin square z. And f fourth dash of 0 is equal to, when you substituting the values, you will have this is equal to 6, that is not equal to 0. So here you can see that here z equal to 0 is a 0 of order 4. Why? Because f of 0 0, f dash 0 0, f double dash 0 0, f triple dash 0 0, f fourth dash 0 not equal to 0. Okay. Similarly, you can see that z equal to plus or minus 2 pi, z equal to plus or minus 4 pi are 0 of order 4. Okay. Next, we have an important theorem. The theorem says the zeros of an analytic function f of z which is not identically equal to 0 are isolated. Now we can move to the proof now. Suppose f of z has a 0 of order n. The Taylor series of an analytic function f of z at z equal to z naught is f of z equal to sigma an into z minus z naught whole raised to n, where n varies from 0 to infinity. So this is equal to sigma am into z minus z naught raised to m, where m varies from n to infinity. Since f of z has zeros of order n, so f of 0, f dash 0, etc. f n minus 1 dash of z naught equal to 0, but f n of z naught not equal to 0, and here a n not equal to 0. Now when we expanding this is equal to a n into z minus z naught raised to n plus a n plus 1 z minus z naught raised to n plus 1 plus etc. Now you can take that z minus z naught raised to n outside. So inside the bracket we have a n plus 1 into z minus z naught plus etc. Okay, so we can represent this as z minus z naught whole raised to n into g of z. Okay, now what is the value of g of z here? Here we have g of z is equal to a n plus 1 into z minus z naught plus etc. Okay, where g of z naught equal to a n and which is not equal to 0. Thus we have f of z is equal to z minus z naught raised to n into g of z, where g of z naught not equal to 0. Since an analytic function is continuous and because of the continuity also g of z not equal to 0 in some neighborhood of z equal to z naught, therefore z equal to z naught is isolated. Therefore z equal to z naught is isolated, and hence the proof. Okay. Next theorem, poles and zeros. So this theorem says let the f of z be analytic at z equal to z naught and have a 0 of nth order. 0 of nth order at z equal to z naught. Then 1 by f of z has a pole of order n. 1 by f of z has pole of nth order at z equal to z naught, and so does the function h of z by f of z provided h of z is analytic at z equal to z naught and h of z naught not equal to 0. Okay. Next we have analytic or singular at infinity. F of z is analytic or singular at infinity if f of 1 by z is analytic or singular. For that purpose, we define the function f of 0 equal to limit f of 1 by z as 1 by z tends to 0. If this limit exists, f of z has an nth order 0 at infinity if f of 1 by z has such a 0 at z equal to 0. Okay. Now we can consider functions analytic or singular at infinity, entire and meromorphic function. So let us consider some points here. F of z is equal to 1 by z square is analytic at z equal to infinity. Why? Because f of 1 by z equal to z square is analytic at z equal to 0. F of z has a second order 0 at z equal to infinity. F of z has a second order 0 at z equal to infinity. Now consider the second one. F of z equal to z cube is singular at z equal to infinity. Why? Because f of 1 by z is equal to, what is f of 1 by z? This is 1 by z cube, has a pole of order 3 at z equal to 0. Now we can consider another example. Example number 3. F of z is equal to e raised to z. It has an essential singularity at z is equal to infinity because f of 1 by z is equal to e raised to 1 by z has essential singularity at z equal to 0. Now f of z is equal to sin z has essential singularity at z equal to infinity because f of 1 by z is equal to sin 1 by z has essential singularity at z equal to 0. Now f of z is equal to cos z has essential singularity at z is equal to infinity. Okay. An analytic function whose only singularities in the finite plane are poles is called a meromorphic function. So a meromorphic function means an analytic function whose only singularities in the finite plane are the poles. Example, tan z, cot z, sec z, cosec z, rational functions with a non-constant denominator. Okay. Now we can move to some more examples now. Determine the location and order of zeros. order of zeros. First function is sine raised to 4 set by 2. So we have to find the zeros, we have to equate our function to 0. That means sine raised to 4 set by 2 equal to 0. That means sine set by 2 equal to 0. That means set by 2 equal to n pi. So set is equal to 2n pi, where n belongs to set. Okay, so we have set equal to 0, plus or minus 2 pi, plus or minus 4 pi, etc. are zeros of order 4. Etc. are zeros of order 4. Now another example. Z raised to minus 2 sine square pi z. This is same as sine square pi z divided by z square. Now f of z equal to 0 implies sine square pi z equal to 0. That means sine pi z equal to 0. That means pi z is equal to n pi. Equal to n pi. That means z is equal to n, where n belongs to z. Here n not equal to 0. So we have z is equal to plus or minus 1, plus or minus 2 are zeros of order 2. Okay. Now let us stop now. Thank you all.